Okay, guys, elimination. Let's move towards coming to the home, around the corner. All right, down the stretch they come. Took the derby time, yeah? Elimination. Those leaving groups go. Five.
Can you hear me now?
Okay, let's see where we left off then. If you have a great leaving group, okay, we're looking at, what are we looking at? We're looking at whenever you can do both substitution and elimination. How do you make the decision? Well, sometimes you can do both. Many times you can do both. If you have a great nucleophile, you're going to do substitution. We showed an example here. Same substrate, HBr, going to give substitution. Br minus is a pretty good nucleophile. F minus is not a good nucleophile. It's actually a better base. You like as a base and do the elimination. Okay? This is a relative comparison. Yes, it is. Both of these reactions have common intermediate. I mean, things are there. Another example of this. If you take this alcohol here and treat it with sulfuric acid, what's going to be the product? This is not shown. You've got to show the product. Well, you got a leaving group. Potentially, protonate the leaving group, make it protonated oxygen. Okay? What's going to be the product there? We know we can protonate, ionize, make carbocation. Right? Make carbocation. From there, though, we can eliminate or substitute. What's the fate of this? What can happen next? Hopefully everybody can get here. You envision getting here, right? Okay? What can happen here? Rearrange? Yes, certainly. We can do a hydride shift and rearrange to a tertiary cation, new H up there now. Okay? Well then here, same question. What could happen now? Nucleophile could add to cation and give us something bonded there, and that would be a substitution product. Because the OH is left, and then if we added something here, that'd be something new. So the OH is gone, and we got something new in place of the OH. No matter where it's bonded, it would be substitution. But what else could we do here? Instead of something added to the cation, we can also have a base, all right? Something with a long pair can take the H, and these electrons move in. That's the fast beta elimination. That's the second step of a... If we do this, the overall outcome is an elimination. Because the oxygen is left, and we haven't replaced it with anything. It's just gone. We also removed an H. It's an elimination outcome. What does this give? It gives us here, right? What mechanism did I just do? Elimination, everybody agree? Formula of this versus this, we've removed water, we've eliminated water. Okay, by what mechanism? E1, right? Okay, E1, it's probably written over there. This is a common reaction of alcohols. Common reaction of alcohols. To treat them with acid and to eliminate water. To remove water, what's the general term for that? So I've got a potato and I do something to it, remove all the water, I just dehydrated it? Yeah, we just dehydrated this alcohol. Is that written over there? First word, I think. Terminology. Common reaction of alcohols is to dehydrate them by E1 mechanism using acid. To make the leaving group better leaving group. What's the base in this reaction? Or let me ask this first. Why not substitution here? First, okay, and what's the base? Base in this reaction would be what? HSO4 minus. Now, I've always just been able to show that condensed. Maybe I shouldn't, because we really don't want to show anything condensed, especially over here. But I've always done that because it's polyatomic. It takes a lot of ink to draw it out. All right, so I've just, all right. Yes, and we reform sulfuric acid here. Okay, this is catalyst. It takes the H back. This is a lousy nucleophile. It will never add to the cation to give a substitution product. Only your halide anions will from the strong acids. Sulfate, actually remember when we did polymerization, we had to use an acid that would not add to the cation. We want the alkene to add again to the cation. The alkene keeps adding. So we didn't want to use HBr and HCl. We had to use sulfuric acid because this anion will not add to cations. It's a poor nucleophile. If we use a poor nucleophile, we're going to get elimination. That's what's going on down here. Common reaction of alcohols. Guess what? This reaction is covered in Organic 2. I covered it at the very beginning of Organic 2. But when I do, I'm like, okay, this is mainly a review. Because at that time, we're focusing on the reactions of alcohols. Right now, we're focusing more on general mechanisms, and this is an example. Okay, common reaction of alcohols, dehydration by E1. On the other hand, if we did the same substrate reacting with HI, well, proton, we got I minus is potential nucleophile. Good nucleophile? Bad? What do you think? Good nucleophile. So, substitution. And by the way, I showed a product that was not rearranged. I minus adding here. Is it reasonable for us to also, if I showed that product, can you guys see? If I said that instead, you see how we get that instead? That's from the rearrangement. Again, I think we said it last time. I did not say it the first time, but I should have. Anytime you can rearrange, you want to show that as the product. So I actually should have showed this, but that requires the explanation of rearrangement. I'd rather you predict the rearranged product. Okay. That comes from the non-rearranged cation. But better nucleophile gives substitution. It's going to be more favored product. Make sense? Questions? This we've already really looked at, but slight little difference here. A more statically hindered base will favor elimination over substitution. So you had this compound, and you wanted to do an elimination. Which base would you use for this? Of the three choices. Well, if you read it, yes, that's here. Why? Why? Do what? Not the same as, yeah, it's strictly him, but why would you use that one?
Because it won't add to the molecule. It won't substitute.
Right. Ammonia is a base. But ammonia could come in here and do a substitution. We don't want substitution here, we want elimination. So could hydroxide. Less likely to do substitution. Any of these would do, the substitution would be SN2, because they're all strong. And we know SN2 is largely governed by sterics. It's going to have a difficult time doing SN2. We don't want SN2. Now, before we looked at this and said this is going to give more of the Saint-Seth or Hoffman? Hoffman. But see, in this example, there's only one alkene you can make. The only alkene you can make is right here, because there's only one beta hydrogen. One type of beta hydrogen. So we're not having to worry about getting Hoffman versus Saint-Seth. And so this is a choice of base you would have to limit the possibility of any substitution. Make sense? Okay, G. Not sure what H was, but I'm sure it was some well-worded heading. G. Clever ways to make ionization. We're looking at some miscellaneous things through the end of this handout. Clever ways to make ionization of an alkyl halide to the chromocation easier. Okay? An alkyl halide. How do you make OH a better leaving group? Protonate. Make it more broadly, make the oxygen positive. Protonation is the most common way. I could show you another little tricky way, but it's the same. It's making the oxygen positive. Then it can leave. Protonation is the most common way. How do you make halogen a better leaving group? We've never had to, have we? We just said it's a good leaving group. Can you make halogen a better leaving group? Yes. Here's a clever way to do that. We can use a Lewis acid, not a proton acid. You don't make halogens better leaving groups by protonate them with acid, not proton acid. But you can use a Lewis acid, and you all know what a Lewis acid is, right? What's the definition of Lewis acid? Okay. They donate what? No, Bronsted-Lowry acid donates hydrogen. What does a Lewis acid do? Doesn't donate it.
Take electrons.
It accepts a lone pair. Very common one with halogen is silver ion. It's a very common reaction here. We have this substrate. Ultimately, we're eliminating HBr. Doing elimination here, yeah? Okay, is the base strong or weak? That is the elimination E1 or E2? I'd ignore this for a minute. Just water. Weak, E1. So what's the first step of the mechanism? Leaving group has to leave. A little bit of heat maybe helps this. You remember the first time we saw a leaving group leave, you all were like, can I do that? I know you were like that. Right? Can this just leave? And I had to show you, well, HBr, you put it in water, what happens? It just leaves. But how fast is that? It's not super fast. In fact, if you got a strong nucleophile around, that's slow enough to allow this to come in here and kick it off first. Here I come. I'm not waiting on you to ionize. How fast is it? Well, sometimes the ionization can be slow and you want to make it a little bit faster. A clever way to do that is include silver ion. Silver plus ion. Okay? NO3 minus, right? Now this is not going to be your base here, okay? This is not a good. That's the anion of nitric acid. Nitric acid is a strong acid. The conjugate base is thus weak. But it's an anion, and Stephen said all anions are strong. Yeah, but we also said there's exceptions, and you know the conjugate base of a strong acid is weak. This is not going to do anything here. This is a source of silver ion. When you go to the stockroom and say, give me some silver ion, it has to come with an anion, right? It has to have an anion, just like your Big Mac has to have for us, all right? So what counter anion do you want? The reason it's nitrate is because in Gen Chem you learned that most silver compounds are insoluble. Silver bromide, soluble in water? No. Hopefully you learned some solubility rules. Silver halides, lead halides, not soluble in water. What do you know about nitrates? Soluble in water? I don't know if the solubility has changed in the last few years, but I think all nitrates are soluble in water, right? Yeah, silver nitrate's soluble in water. That's why it's the nitrate's used. All right? It's a silver ion, a source of silver ion. Silver ion, now it's somewhat very analogous to proton, H plus, silver plus. These electrons can bind to the silver. Instead of, okay, what's going on here is silver has d orbitals. And the halide, which is not basic, it's not going to interact with protons, but it will interact with silver. The d orbitals help it. Okay, much better interaction. And the silver ion is accepting a lone pair, so we call it a Lewis acid. It's also a Lewis acid, but we more appropriately call it a Bronsted-Lowry acid. Lewis acid. And we can get something, if we show this covalently bond to silver, the bromine is now positive. And these transition metals can make covalent bonds. Okay? They're sort of in between. You never want to show sodium with a covalent bond. But sometimes transition metals, okay, they're transition, they're in between. Some covalent nature. Now it's like we made the bromine positive, right? Now if it ionizes off, now, do you think it's going to be more prone to wanting to get these two electrons back as a lone pair? Want to leave? How do you make oxygen a better leaver? Make it positive. We made the bromine positive. It's going to leave easier now. And when it does, what do you get? It's going to be Lg. What is this? A silver bromide. And what do you know about the solubility of silver bromide in water? Not soluble. This precipitates. That helps drive the equilibrium bit. So it's analogous to protons, except silver ion is more common with halogens. Silver ion. Silver d orbitals. Where's silver on the periodic table? Under copper? Right? Copper, silver. What's next? Copper, silver, gold. Right? Okay, there we go. You should look through this. What eventually takes the H? You got to eliminate. You're going to get cation here. Something takes the H. I'm showing the nitrate taken. So it is acting as the base, but the weak base. If it was a strong base, we'd be doing SN2. It's E1, right? Carbocation chemistry. Or you can show water taking it. If water took it, you would have H3O plus, and the nitrate would just be nitrate. But guess what? That's actually more correct, because how does nitric acid exist in water? Like that. Strictly more correct, and I've been over that ad nauseum. Okay, clever wing. It's a little silver ion. You can actually use the silver as a chemical test for the presence of ionizable halogen. What? You're right there.
Secret agent.
What?
Your secret agent.
Secret agent. Can also be used as a chemical test because the silver halide precipitates, something you can see. Say, ha, I got to precipitate. Which compounds below would give a positive silver nitrate test? That is, would give a precipitate with silver nitrate. What's really the question here? How can we restate the question something else? What are we really looking for? The question is really, which ones are going to form carbocations after the bromine goes and teams up with the silver? Which ones?
Third one.
The third one? What? The third one or this one? Okay. Why that one?
Because it's an action item.
Once we make the silver halide, what are we going to be left with? That bromine leaves, Br minus leaves, teams up with the silver plus, and we're left with carbocation, right? Do you expect that this bromine, is this bromine ionizable? Is it going to leave and form this? It's a tertiary cation. Not only is it tertiary, it's resonance stabilized. It's a very good cation. Yes, it's going to do that. Well, what about this one? Right? Talking about the bromine ionizing. You really forget about the silver. It's once the Br minus comes off, it pairs up with the silver and makes silver bromide. We're really saying, the question here is really, which of these can ionize? Lose the Br minus. And the Br minus ends up forming silver halide. All three of these can. This one cannot. All three of these, the halide is on a tetrahedral carbon. And none of them are primary. Everybody agree? No, we're not making primary cations here, right? But this one would not. That bromine's not on a tetrahedral carbon. You're not going to make a cation here. It would not be resonance stabilized. It would be worse than a primary carbocation. Those three. Of those, which would give the precipitate of silver bromide the fastest? Which cation would be best? It's tertiary and it's resonance stabilized. Any questions about this? You guys able to assess potential carbocations that will be forming here? Nobody questions the fact that I said none of these would be primary carbocations?
Well, the last one would be the shift down.
Exactly. When the last one ionizes, we give that cation. Would you call that a primary carbocation?
Yes.
Well, we know it's a hybrid, right? We can draw a resonance structure, right? Up here, windshield wiper up, cation there. You see, when I look at this, I see a secondary cation. So who's right? I'm calling it secondary, you're calling it primary. The cation is a blend of these. It has characteristics of both. Right? It's a delocalized cation. So just calling it a primary cation is not telling the whole story, like you said in your very first comment. Anthony?
So on the very last molecule, let's say, well, on the very last molecule, the double bond, let's say it was, I guess, windshield wiper down. So that way when you get your primary carbocation, it does a hydride shift. It would end up being resonance stabilized. Which one of the two would be better? The middle one or the right?
I didn't understand this. Here's the cation, and you do what?
Yes, let's say we windshield wiper the alkene or the double bond down.
What do you mean, this way?
Yes.
No,
So
you
no,
can't-
I'm saying
you
like let's say that's what we started with the actual double bond being down there. So it would end up doing a hydride shift. Yeah, exactly like that.
Oh, you do here.
Yeah, so it would
And
end up
instead
doing
of the pi bond there.
So when you do that, when you make a primary carbocation, it would make a tertiary carbocation.
Yeah, but you did two steps up here. First you made a primary cation, which is bad. This is not resonance stabilized. Now, if it did a hydride
Yeah,
shift,
that's what I said, the hydride shift, and then it would be
but the
resonance.
problem is though, you got a transition state leading to this. And that transition state leading to this is going to keep this from forming. So you're never going to have the opportunity to do your hydride shift.
Well, then how come you can do it on the one down there?
Where?
It makes a primary carbocation on there also.
Because this is resonance stabilized.
Okay, okay.
It's not a hydride shift. As soon as the bromine comes off, it is neither of these.
Cool.
As soon as the bromine leaves the molecule, as soon as the bromine leaves, that's what it looks like.
Okay, cool.
But we just did not draw that immediately because that's hard to draw. We do this resonance structure stuff. And we know these are fake. That's one thing. Here's the true thing. As soon as the bromine leaves, it's this. As soon as the bromine leaves in your molecule, it's this. And that's a lot different from this. This is delocalized. The charge is delocalized. Yes, you can theoretically get to something better, but you're never going to get to that bad thing first. Okay, those three would, but that would be for fact. Basically, which cation's best? That's the second question. Of the three cations that are going to form, that would be best. Because not only is it resonance stabilized, it's got characteristics of tertiary secondary, where this one has characteristics of primary secondary. It's a resonance structure thing. Other ways to make halide a better leading group. We've mentioned this before a little bit, is use a polar solvent. Look at these two reactions. Same substrate with leaving group. We're trying to do the top reaction, we did substitution. This oxygen replaces the bromine. All right? On the right hand, bromine, that's the oxygen. Bromine, oxygen. Of course, the oxygen is bonded to other stuff. Substitution product, right? Mechanism for this Rupp-Top reaction. Just these two, and that's it. And solvent. Mechanism. Substitution, right? SN1 or SN2? SN1, right? There's no strong nucleophile. That's a neutral alcohol. Weak nucleophile. Okay? What's the first step of this mechanism? Leaving group leaving. How can you make it leave faster? How about some silver nitrate? Yeah? Okay. Another way is to use a polar solvent, such as acetonitrile. Anybody ever use acetonitrile in lab? Okay. Or DMSO, dimethyl sulfoxide. We've mentioned it before. It was on the handout during week 1. Both are polar aprotic solvents. Okay. This has got to ionize. Right? That's your rate determining step. What type of solvent promotes formation of ions? Polar solvent. That's why when you put HCl in water, it ionizes. Polar solvent. If you try to do this reaction with a nonpolar solvent like hexane, nonpolar, right? The reaction ain't going to work. It ain't going to work because hexane is not going to facilitate this happening. If this formed in hexane, it would be treated badly by hexane. It would be ignored. It would be treated as an outcast. It ain't going to form. If it's formed in a polar solvent, the polar solvents will love it, take care of it, nurture it by coordinating with it. Okay? Polar solvent facilitates ionization. You already knew that, though, right? Deuterium isotope effect. Moving on to the letter H. We'll probably not get into that, but let's see before we end here. Any last questions? We'll finish up this handout next time. Okay? And then we may we'll likely do UV Viz. Any last questions, guys? Video key posted later today. Have a good day, guys.
Yeah,